Oh, I also did take attendance. Is everyone who's not here? Laura, oh yeah, okay. So that's 4, 7, 10, 12. Okay. Yeah, we're putting up stuff on the recording, just so you know. Okay. Okay. It's good for you. Yeah. Hold on a sec. This attendance system's taking a while.
Like rain, quite healthy, except to have like 40 grams of sugar.
Okay, here we go. All right, so for synthetic division, um, it's not just for dividing, but it's also for evaluating a function. So of course, if you want to evaluate f of -3, I mean, yeah, just plug in -3 and just work it out, right? Okay, I have a struggle with writing threes here. Oh, so many threes. So you could do all this work, right? Um, and I've never really asked this question because this is kind of just a dumb question. I mean, I know you guys can do this. This is more of an algebra one question. But if you were to do this without a calculator, that could be a little painful because you got to do -3 cubed, which is -27 times -3, which is -81. But then you got to do all the other computations, all these negatives, and you could easily make a mistake. So you could do all that, and it's going to be some number. Or you could do this. You put -3 off to the left. You put all the coefficients aside. Anything that gets skipped over along the way, I'll get out of the way. You put the coefficients down, and you just do the process of synthetic division, right? So it's actually synthetic substitution. So you guys remember what we do? We bring the 3 down, and then what do I do after that? Multiply, and then what do I do after that? And rinse and repeat. And what do you guys' final answer? 6. So that means that f of -3 equals 6. Now, what's actually happening here? Essentially, what you're doing is you're doing f of x divided by x plus 3 with 6 as the remainder. That's really what we're doing. Now, what if the remainder was 0? Then what would that tell me about x plus 3? So that x equals -3 is a 0 or x plus 3 is a factor. So this is what's happening here. This is called the remainder theorem. And I think it's described somewhere in the notes. It's called the remainder theorem. There's also something called the factor theorem, which states that the remainder is 0, then x minus that number is going to be a factor, as it should be, because there's no remainder. And that's where we're going to be working on an example 11. And I think it's kind of mentioned. Yeah, it is mentioned here in the notes. I'm not going to do the proof, but yeah, it does say that the remainder r gives the value of f at x equals a. That is r equals f of a. There you go. But if r equals 0, the next minus a is a factor. That's part of the factor theorem. So that's going to be the case for example 11. Now, I believe in Mr. Band's class, he had you guys do this by trial and error. Am I correct in assuming that? I don't believe in that. That goes totally against my core values as a teacher. I don't believe in trial and error. Granted, there's a way you can figure out what options could work using the rational zero test on the next page, or sorry, down below in the page. But I would give you a 0 because I just think trial and error is just a waste of time. You're not really learning anything doing that. So don't worry, I'm not going to do that to you guys. But I will do some example 11 and say, yeah, show me that this is a 0. Okay. Yeah. You know, I'm not going to make you guys do this trial and error nonsense. So if you're told 1/2 is 0, what do you expect the remainder to be? 0, right. So how do you prove it? Just do the synthetic division, right? Bring the 2 down, multiply, add, multiply, add should all work out nice and neatly. So you get that right. Now, they say use that information to find the other zeros. So I've now broken down this polynomial. See what you've done. What does all this represent? This is f of x divided by what? X minus 1/2, or technically speaking, 2x minus 1. But we'll say x minus 1/2 because the 2 is still there. Yeah, we'll say x minus 1/2. So that's what this represents. So this is 2x squared minus 14x plus 20. Without realizing it, you've actually done a fancy way of factoring. That's what you've done. You've actually factored out x minus 1/2. You've broken down the polynomial down to a quadratic. What should I do next to solve this? Yeah, factor if we could. What can I pull out? Okay, and hopefully, yes, this is factorable. What do you get when you factor it? Good. Yeah, that's a pretty easy one. And of course, you get x equals 2 and 5. So those are our other zeros for this function, right? So, okay. So we're pretty comfortable with that. That's good, right? Um, the rational zero test, this has really no place in calculus, but I'll just talk about it briefly so you know what's happening here, in case you guys forgot. Um, P and Q. Do you guys remember what P represents?
Oh, wow.
Yeah, all factors of a sub 0, which of course is your constant, the constant term that does not have x. And what does Q represent? Yep, all factors of a sub n, which is your leading coefficient. So what this is telling us is that, excuse me, your zeros of the function that are rational numbers, meaning the ratio of two integers. So if 1/2 of 0 or 3/4 or 2 or -5 or whatever, they take on that form. They'll take on that form. And here's the thing. It's actually the possible rational zeros. There's a likelihood that I could give you a function and you do this P and Q nonsense. No, it's not nonsense, but you do this P and Q business and get all these possible rational zeros, and none of them would ever work. That's the total possibility. I won't do that to you guys because that's cruel. That'd be really cruel. And again, I don't like trial and error. But you could get a polynomial that looks like this, right? That's a polynomial function. Is that crossing the x-axis? So how many rational zeros does it have? None. There could be possible rational zeros using the P and Q thing, but none will work because all the zeros here are going to be complex. So that's why I don't really like this. It's just a cool thing to see and understand. Like, hey, this is what could happen. But yeah, we're not going to spend too much time on that. Um, I'm not going to waste my time because this doesn't really have much place in calculus. So we're going to skip over a lot of this.
We still do the homework.
No, I'll tell you. Actually, once we finish what we do, I'll tell you what I want you guys to work on over the weekend. Because there's some things I skipped over. I know the other day. Um, so yeah, let's just skip it all over. Let's just go straight to and I'm actually gonna skip a lot of things here. I don't care about complex numbers, by the way. It has no place in calculus also. So we're gonna skip all the complex number stuff. So we're gonna skip a lot of stuff here. We're gonna skip all the way to page 17. Okay. This I care about because this is dealing with asymptotic behavior. It's dealing with limits. It's dealing with increasing, decreasing behavior. I care about this. So, and I think we'll be able to finish this off today as I take a look. Yeah, there's a lot of rational functions. Geez, there's a lot actually. But this is like what we don't finish that I think would be fair for homework. So, okay, so let's get started over here. Okay, rational functions are ratios of polynomial functions because you're doing one function, one polynomial on top of another. The simplest one is 1 over x because 1 is 1, x is x, right? The graph is right there. What's the domain of 1 over x? So So 0 is excluded. Now, formally, we have to write like this. I am going to make sure you guys are writing things in interval notation. If you were to say all real except 0, I'll take out points because I'm going to specifically ask for interval notation. You have to get used to that. So again, we're preparing for calculus, right? AP calculus specifically. What's your range here? Same thing, right? All real but 0. In the union, you're uniting both intervals. Okay, the continuity part. This is a little tricky. This is not a continuous function, by the way. It's not continuous on all real numbers, but it's continuous on its domain. Because does the domain include 0? No, right. So you will say it's continuous on the same interval yet again. I know it's kind of a weird thing because in essence, it's not continuous because it's clearly a break at 0, but that's just because we're assuming continuity over real numbers. But if you say, well, is it continuous on its domain? It would be. Now there are some instances when you're not continuous on your domain. You guys remember you don't have to write this down. It's more for your own curiosity. You guys remember this from August or September? So this is a step function or the greatest integer function. So what's the domain for the greatest integer function? All real. However, is this continuous on its domain? Nope. So that's an example of a function that's not continuous on its own domain. But 1 over x is continuous on its own domain because 0 is excluded already. Is there a y-intercept here? Nope. Is there an x-intercept?
No.
Nope. Yeah, no way can y be 0 because y is 1 over x. And for a fraction to equal 0, you need numerator to be 0. But numerator is stuck at 1. So forget about it. It can't happen. So armed with that knowledge, we can handle these limits here. So this right here is going to be for end behavior. And this right here is going to be for what we call the infinite discontinuity. We talked about this the other day. And disc for short for discontinuity. So asymptotic behavior is closely tied to limits. We're going to go really hard with limits next week. So if you look at the end behavior, as x approaching negative infinity, what's y doing? Go 0. And likewise, when you're going to the right. That is what gives rise to horizontal asymptote. It's not a boundary you can't cross. Sometimes it is. Many times it's not. You can cross horizontal asymptotes in the middle. 100% you can. It's more about the ends of the graph. So we're getting a deeper knowledge now about asymptotic behavior. So the horizontal asymptote is actually a limit as x approaches positive negative infinity. That's what all it ever is. It's looking at the ends of the graph. So what are the horizontal asymptotes here? Well, it's both y equals 0. Now, the vertical asymptote is also a limiting situation. As you're approaching 0 from the left, so we call these here, running out of space here. This superscript, was a little surgical precision. Circle that very nicely. We call that a one-sided limit because you're looking at the limit from a certain side of 0, either from the right side or the left side. So I call this one the left-hand limit. And I call this one the right-hand limit. So LHL stands for left-hand limit, RHL stands for right-hand limit. So as you're approaching 0 from the left side, what's y doing as I approach 0 from the left side? It's going down forever, correct. What's happening if I'm approaching 0 from the right side? Pause infinity, very good. When this happens, that gives rise to an infinite discontinuity because it's causing a break in the graph or discontinuity and there's an infinite nature to y. So when this happens, that is what a vertical asymptote's all about. It's not about, oh, it makes a bottom zero. Yes, you're taught that. That's not really what it is. It's causing the graph y to go up or down forever as x approaches a certain number from the left or right side. So in this case, we call this a vertical asymptote, which happens at x equals 0. That's the true definition of these asymptotes using a calculus lens. Now indicate the intervals of x for which graph of f of x is below the x-axis or above the x-axis. Well, that's pretty obvious. From negative infinity to 0, it's below. Non-inclusive, of course. And 0 to infinity, it's above. Okay, so that's just kind of giving you a review of asymptotes, but also just approach from a limit perspective. Now, when you guys saw this last year, did Mr. Band talk about limits or as x approaches? Did he kind of okay? So and that's okay because it's algebra 2, right? Now we're going to talk about limits in this class. So, and these are things that are assumed you know when you move on to AP Calculus BC. You do not review this again. You'll have a summer assignment, but you're learning this now with me because we don't want to repeat these efforts next year. We actually are very intentional to make sure that there are no duplicates from this class and Ms. York's class. That we actually talked a lot last year where, okay, she knows what I'm doing, so she'll assume that and build on that knowledge. So that way you guys are learning new stuff in the fall. I don't think we need to do some Desmos. I think we could handle this by hand. I think we could I think you guys can handle this. So we do know there's a certain value of x that's not okay. What value of x is not okay? 2, right? So I'm going to draw a vertical asymptote right here. Okay. So I kind of already know that. Now the horizontal asymptote, this is where we're going to use numerical reasoning. You can memorize this process. And you guys probably saw this last year, I think, like ax to the m power plus dot dot dot. Like, do you guys learn about the generalizations for horizontal for asymptotic behavior? Like if m is bigger than n, m equals n. Okay. Actually, I don't like that because then students become reliant on memorizing. I'm like, well, what was it? Was m equals n, m equals less than n, greater than n? Like they're just like, and you go a little crazy, and then you got like all these other things in your life. You got 5, 6 other classes, and you got sports, and you got your life and your families, and the 49ers are in the weekend. No, I was just kidding. Or Stranger Things. No, you got all these things going on, right? And you're trying to memorize this one little thing in this one class in this one part I have in your life. But let's not do that. Let's not memorize. I don't like it. I would much prefer you guys understand why these horizontal asymptotes work. Just yes, there's a generalization, 100%. But I would much prefer tell yourself, what does y do when x is large? What if x is 1,000? What do you have? You have 3,000 minus 7. That's 2993. You have 1,000 minus 2. It's 998. If I divide 2993 by 998, that's pretty darn close to what number? Well, you're doing something times 3 over something. It's gonna be very. If you're plugging in 1,000, right? We had 29. I'm sorry, I'm just throwing numbers your way. So let me write down. If you divide those two numbers, what's that gonna be pretty close to? 3, yeah. So I'm gonna draw a horizontal asymptote at 3. And just gonna get ever closer to 3, right? Now, the range is tricky because it actually helps actually have the real graph in front of you. Could y equal 3? Could it equal 3? Well, the best thing to do is set the equation equal to 3 and see what happens. Could this expression equal 3? No, it cannot, because what's going to happen?
Yeah.
Yeah, you get nothing. So that's going to be excluded from our range. Now, sometimes that can happen. And in order to prove it, you'd have to set the expression equal to 3. We'll have more complex rational functions in a moment. And we can cross the horizontal. You totally can. It's really about the ends of the graph. That's all it's about. We are going to be continuous on its domain. You know that for sure. Y-intercept is easy. How do I find the y-intercept? Yeah. So you get that. So we're totally going to cross over here. 3.5. I went too high. I went to 4.5. My apologies. Is there an x-intercept? How do you solve the x-intercept? Correct. If you set f(x) equal to 0, and here's the thing, again, the memorization part is what kind of drives me nuts. I mean, I've taught at level pre-cal, which obviously is a class fun group of students, but they want to memorize, right? And they figure, well, wait, you said the bottom equals 0 and the top equals 0. How do I find the x-intercept? It's like, well, my eyes like, dude, you've had like algebra 1, algebra 2, and you're asking this question, but it's okay. Math is not their jam. It's all good. But you guys, I know math is your jam, because if you think about it, in order for that expression to be 0, what has to be true about the top? It has to be 0. The bottom, who cares? The top needs to be 0, and that happens at 7/3. Right. So you guys should know to set top equals 0, which is right here. Okay. And then usually it's a good idea to do a sign chart just as an extra layer. For example, I'm gonna when you do a sign chart, these numbers are awfully close together. When you do a sign chart, you pick what we call the critical points. The critical points are what make the top and bottom 0. Why are they critical? Because they'll cause y to go from positive to negative or vice versa. That's why they're critical. They're important. And what causes, how do I find them? Just set the top and bottom equal to 0, right? So if I plug in anything larger than 7/3, say 10, well, we know it's positive, right? And here's the thing. 3x minus 7, x minus 2. Are there any exponents next to those factors? If you have this is raised to the 1 power, and that's raised to the 1 power. Those are odd exponents next to each of those factors. So we expect an alternation in sign. So I don't really need to test it because I know the signs will alternate. Because now if any of those factors were even, then I wouldn't change the sign. Like let's say 3x minus 7 is 3x minus 7 squared, then it'd be positive at that partition, right? I don't see that. So I know the graph's going to look like this. And you have the asymptotes for a reason, right? They're going to go against them. So now I can answer this limit stuff. The limit as x approaches negative infinity is what? And positive infinity? 3. And if I approach 2 from the left side, what's that going to be? Yeah, and from the right side, yeah. So I call this my LHL and my RHL. But it helps to actually look at the graph, right? And the sign chart, excuse me, this is my voice. The sign chart helps too. I mean, yeah, sure, plug in 1.9999, plug in 2.001. But if you don't have a calculator, it's going to be hard to do. But you can kind of imagine if I plugged in like 2.001, sure, the top is negative, bottom is positive. If I plug in 1.9999, the top and bottom are both negative, so it's positive overall. And when am I below the x-axis? Definitely from 2 to 7/3. And you can keep it as an open interval. And you're positive from negative infinity to 2. And from 7/3 to infinity. And actually, I don't want to include the 7/3 because when x is 7/3, y is 0. Is 0 positive or negative or neither? Neither. Yeah. And so then you're not really positive or negative, right? So we want to include them. So that's the way to analyze this graph really well. And that's what I care about. I want to make sure you guys have a deep, intimate knowledge with rational functions before we apply calculus principles. And before we start doing all this calculus stuff, you really got to know these graphs really well. That's the intention of this week. We already did that for polynomials, and we did some, synthetic division stuff, fine. But the complex number stuff, the other stuff, the P and Q stuff, I don't care about. I could go over it, but it's not relevant to what we need to do in this class. So, does that make sense how that one's done? All right. Let's talk a little more details. Let's talk about holes. We got to talk about holes as well. We'll talk about horizontal asymptotes a little more. We'll generalize it. We'll talk about slant asymptotes. Um, so we have a little more nuts and bolts to cover. And I'll probably do maybe one more graphing example, and then the rest I'm gonna let you guys do. So I know we got a 75-minute class. We got a lot of time today. So I still need about 20 or so minutes, and then I'll let you guys do the rest of the problems for homework. Excuse me. So let's talk about graphing this stuff by hand. Okay. Let me clear some, get some water here. Okay, so graph this stuff by hand. Generally speaking, you have this a sub n x raised to the n power and b sub m x raised to the n power, fine. And you assume that the denominator is never zero, fine. So vertical asymptotes and holes. So very important. We've seen this already now. When x equals a is a vertical asymptote, that tells me that the limit as x approaches a from the left or from the right or both, doesn't have to be both, by the way. It could just be one of these and still consider a vertical asymptote. Like you can have a graph like this, by the way. You don't have to write this down, but you can have a piecewise function. I could make up a piecewise function like that. That's still a vertical asymptote. Because if let's say this is at x equals 2, what's the limit as x approaches 2 from the left side of this function here? Positive infinity. That's good enough to say it's a vertical asymptote. You don't need to have the other side. As long as you have one side, that's why it's saying plus or minus and the word or. You don't need both. That's still valid to be a vertical asymptote. I know it's kind of a weird graph. It's a piecewise function, but yeah, that could happen. Um, and again, the quicker way to do this to set the bomb equal to 0, right? That's a quick and easy way. So we know that already. So here for this example, 1 over x plus 5, what's my vertical asymptote? X equals what? Yeah, that's easy, right? We're done. But technically, what's happening, if x is negative 4.9999 or x is negative 5.01, what's y doing? It's going haywire. It's going up or down forever. That's really what's happening. Okay, now you could have something called a hole as well. For example, you don't have to write this down right now, but what if I had 2x plus 10 over x plus 5? Say I asked you to graph that. How do you think that graph's if I were to plug this at Desmos, what would Desmos show you? Yeah, go Lucas. Yeah, it show you y equals 2. But not the whole line, but part of the line. There's a hole at negative 5 because what's happening is you factor out 2 and those cancel. And what do you get? Y equals 2. However, you must exclude the negative 5 from the graph. So that's what we call a hole. More specifically, we call this a point discontinuity. Sometimes also called a removable. So either term is fine, but it's a point that you've taken out or you removed. But a hole is kind of like the informal way of calling it because it is a hole in the graph. You won't really see it that well in Desmos, but if you do mouse over graph and like mouse over to x equals negative 5 really slowly, it'll show you a hole there. And in order to determine it, you need both numerator and denominator to be 0. Both. So you need common factors. That's how you could tell. So in this case, for part A, those cancel. For part B, you get this, and for part C, get this. So what's happening? There's a hole at x equals 1. But here you have a vertical asymptote. And of course at x equals -3, by the way. What's my vertical asymptote for part A? Still -3, right? Yeah, still -3. And then for part C, do I have any holes? No. Actually, no, sorry, you do. My apologies. You do. You do. I'm losing my mind. Of course you do. In a vertical asymptote, x equals -3. How do you find the y coordinate of the holes? Yeah, plug it back in the simplified form. Yeah, that's it. And here this would be at 1, 0. We plug in 1 to the simplified form. So you can't just assume where it makes the bottom 0 is a vertical asymptote. Because what's happening here for part A, by the way, here's what's happening. As x approaches 1 for left and 1 from the right, what will be the limits for both those cases? If we were to actually graph this in Desmos, what's y approaching? 3/4, yeah. Thank you, Teddy. Not positive or negative infinity. When this happens, you get this. What has to be true for the limits for it to be a vertical asymptote? X, the limit has to be approaching what? Positive or negative infinity, right, exactly. So that would be true for part B, right? For part B, that would be 100% true. If I did those same limits for part B, and this is I'm actually kind of doing the stuff I plan to do next week, by the way. So I'm actually talking about right now with you guys. For part B, if I take those x approaches 1 from the left of f of x, and the limit as x approaches 1 from the right of f of x, that's going to be positive or negative infinity, right? Yeah, what is that exactly going to be? Got just my head here. 0.999. Yeah, that's going to be negative infinity and positive infinity. In that case, it's a vertical asymptote when that happens. So that's how you can tell. It's all about the limits. Why you get a hole, why you don't get a hole. All comes down to the limits. You plug into the simplified form. Yeah, but figure that out. I mean, the graph would show it too, but numerically, you could just plug it in. So, yeah, go ahead. Yeah. Yeah, I glossed over that. That's my fault. I imagine like what if x was like 0.9 or 0.999, right? Because if x is approaching 1 from the left side, x is slightly less than 1. If I put like 0.999, that's gonna be a negative value. Of course, it's like 2.999, that's 3.999, right? But that's a small number. If I put in 0.9999, that's negative 0.001. What happens when you divide by a small decimal or small number? If you do 1 over 0.001, it's bigger. Or 1 over negative 0.01, then it gets more negative, exactly correct, like negative 1,000, for example. You 1 over negative 0.01. So as x is closer to 1 from the left side, overall, this fraction here is being more negative. That's why I know it's negative 10. Now, what if I play 1.001? Then it's 0.01, right? So fine, I got 2.0, sorry, if I play 1.01, I have 3.01, 4.01, sure. But then that's gonna be 0.001. So when I work all that out, that's gonna be positive 50.
Imagine all that without like graph, you just like go from.
Mentally, you just kind of do the calculation mentally. Yeah. But really, the sign chart's gonna be the best way. Actually, you know what? What we really should be doing, we should be doing a sign, and we will when we get to some of the other examples. So I don't actually, because you're gonna drive yourself a little crazy to keep doing these mental calculations. So I think a sign chart would be the best way. For example, if I were to do a sign chart for part B, and hold on, Charlie, you had a question?
Yeah, you have to do the limit approaching stuff for every app, so
Oh, sorry, do what? Sorry.
you have to do that for every app. Okay.
No, not necessarily. No, I'm just trying to show you what the difference between holes and asymptotes. That's all. Not necessarily. No, unless I ask for it. Um, but yeah, if I were to do this and those cancel, right? I know I have a positive here, a negative here, and I think they should all alternate, I believe. Yeah. So, so really, what the best thing to do is do your sign chart after you simplify it. Do your sign chart, and because you know that's asymptotic at 1 and -3. So what's happened to the left of 1? That's because it's negative. That's why it's negative infinity. Because to the left of 1, I'm negative. What happens to the right one? I'm positive. That's the best way to do it. Great question. All the factors occur once. So unless they're even number of times. That's it. Correct. Correct. Yes. Correct. Yep. And don't worry, we're gonna get to some examples of that in just a little while. Okay, horizontal asymptotes we already talked about again. It looks, yeah, Beth, yeah, good. Yeah. So yeah, as x approaches positive infinity, if y is approaching some constant, then that's a horizontal asymptote. That's your end behavior. And there's a generalization here, which I said I don't like, but I'll just tell it to you because so you know. Then if n is less than m, by the way, so I call this like bottom heavy because the bottom's heavier than the top. That's y equals 0. If they're the same, then y equals what? The ratio of those two, right? Coefficients. And here I call this top heavy. There is no horizontal asymptote. Instead, you have something called a slant or oblique. Where you have to do polynomial division. You could do synthetic if it's possible. If not, then you could do the long division or the technique I showed you guys a couple days ago. Oblique, hold on, Marie. Oblique asymptotes are those that could be parabolic or really funky. And I think they're called obliques. I mean, I don't really work out, but you have your oblique muscles and they're not really straight. I don't know, they're kind of curved. Maybe that's why it's called oblique. But um, but you don't have horizontal asymptotes. You have to actually do the division to break it down. Because remember, what you're trying to do is you're trying to figure out what does y approach positive negative infinity. When you do the long division, you'll have a remainder, which pretty much goes away, and then you can figure out what's happening afterwards. So that's why we care about doing this long division so that we can actually see, oh, okay, well, this is what it's approaching. So this is going to be the asymptote. The graph's going to behave like that as x approaches positive negative infinity. So we'll do some examples of that in a moment. But that's what's happening for the last part, is that you want to do the division so that you can get the remainder out of the way and really see, oh, okay, it looks like this. So, yes, there's a question. No, remember you had a question? Yeah, yeah. The two different ones. Slant is like a line, So slant asymptote would be like this. Say I have a graph that does this, right? And sure, I could probably have something like this here. So you get that. Now, you could also have the oblique ones. We'll see if we run into that today. I don't know. I have to look at examples. Let's say you have a end behavior asymptote that has like that's quadratic in nature. That could happen if you have like x cubed plus dot 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 over x minus 1, let's say. Because if I divide that, I'm going to get x squared, right? So you could have an asymptote that could look like a parabola. And you can have a vertical asymptote as well. So it means that your curve is going to do something kind of like this. And it's going to follow the contours of that parabola. Like you get some really weird stuff going on there. So it means that on the far left and far right, they're going to be identical to that parabolic equation. How'd you get that parabolic equation? From doing the long division or synthetic or whatever. That's an oblique asymptote because the way the graph is behaving on the left and right end, it's not straight. It would be straight if it's slant. And of course, it's flat if it's horizontal. X-intercepts, that's obviously occur at the zeros of the numerator. And they're not zeros of the denominator, because otherwise that'd be a hole. The y-intercept is a value of f of 0. You know this. The slant asymptote, consider rational functions numerator is of degree 1 or greater. If the degree of the numerator is exactly 1 more, it has a slant asymptote. So like this is a great example, right? And that's going to involve, in order to work that out, how did they get that in the first place? How did they get x minus 2 over plus 2 over x plus 1? How'd that happen? You did the division, right? If you do the division, what do you get? X minus 2 plus 2 over x plus 1. Because these are identical expressions, right? This right here and that right there, those are the same thing. If I graph this, they're the same thing. They're exactly the same thing. But why do we do this change? Why do we care about that? What happens when x gets large? What happens to this little fraction when x gets large? It goes away. It's negligible. So what are you really stuck with when x gets large? That's why the graph behaves that way at the ends of the graph. That's why it's end behavior. When x is going towards positive or negative infinity, you look at this and say, well, if x is approaching positive infinity, I don't care about this little fraction. So it looks like x minus 2. Hence, you have a slant asymptote. Likewise, with negative infinity, if x is approaching negative infinity. That's why we do that. That's why we have this division process to understand how the ends of the graph behave. Now, what if that was x cubed? Sense. Everything else is the same. Now you have a quadratic. Now you got yourself an oblique asymptote. That's parabolic. Because whatever little fraction you have at the end just goes away when x is large. And that's what's happening. So slant asymptotes will help you draw the end behavior of the graph more accurately. Vertical asymptotes, horizontal asymptotes, whole slant asymptotes are all concepts that are a result of finding limits, right? That's what we talked about. Well, we are doing it analytically now. Well, actually, we'll do it more analytically next week. Yes, and we are starting our study of calculus. There we go. Great. So just some, things to keep in mind when you graph rational functions. And the way I would, I probably will actually, I think when I have, this test is not for another month, but in all likelihood, I'll probably give you a rational, I'll probably do a non-calculator section. I'll probably give you a rational function. I'm going to ask you to graph it. They'll ask you to do some calculus to it, like we're doing right now with limits. But I'll do it as parts. I'll say, part A, give me the x-intercepts. Part B, give me the y-intercept. Part C, give me the asymptotes. Part D, give me the holes. Part E, give me the sign chart. Part F, now sketch a darn thing. Oh, and part G, let's do some limits as well. That's how I'd probably do it. So you don't have to memorize this process. I would actually spell it out to you in several parts. But yes, consider factoring, consider simplifying. find the holes, x, y-intercepts, asymptotes, all that stuff. Slant asymptotes, there's going to be some long division. As you can imagine, I could really go pretty deep with this, right? Completing the statements about the limits, all that stuff, sign chart. And that should help you to make it a more accurate graph. Because not just limits, but we're going to be doing derivatives. We're going to be doing other types of calculus principal sets later in the year, but we have to look at through a limit perspective so we can do all this other stuff down the road. Okay, so let me do two more examples, and then pages 22 and 23 and 24 will be homework, as well as some other stuff from the previous page. And I'll tell you which ones to do because some of these things I said were not relevant, so that's totally fine. So let's look at example one. What do you think should be my first step?
Factor.
Yep, 100%. Okay. What are my asymptotes?
Negative 2.
Yeah, I don't have any holes, by the way. Nothing cancels. Even though we should be considered from a limit perspective, we could just do the quick and dirty way. Just like, yeah, we don't see any, canceling. Given how the original function looks, what's my horizontal asymptote? Or do I have one? I do have one, y equals 2. What are my x-intercepts? Yeah, 1 and -1. What's my y-intercept? Good. Thank you, Sophie. Thank you. And we should probably do a sign chart. A sign chart, you should probably look at all the critical points. And here's the thing. I have it fully factored out, right? Look at so here's the quick way. When you guys did sign charts, I think you guys would test every interval? Don't. It's a waste of time. All you need to do is test the far right interval and then ask yourself, is each factor occurring an even number of times or an odd number of times? If every factor is occurring an odd number of times or only happens once, the signs will alternate. So if I plug in 3, is this whole thing positive or negative if I plug in 3? Positive. Okay, is every factor occurring once? Alternate the darn signs. Don't waste your time. Do not waste your time. So, you know how like Mr. Band does like these like time quizzes? Actually, I kind of support that in some ways because he's trying to test the efficiency. I do see why he's doing that. I know it was a stressful, traumatic thing for some of you guys. I get it. I've heard. Trust me, I've heard the stories. Um, But on the AP exam, it is a timed exam and you have to move fast. So I think I want to teach you guys efficiency. You don't need to test every darn interval. Just like test one of them and then like, okay, if one of them squared, fine. If that one's squared, then sure. There's no alternation at 2. Keep it positive between 1 and 2 then. Fine. And alternate afterwards. It just depends what you got going on. So now if I plot all this, see here, we'll go light blue here. And y equals 2. And 1 -1. And 1/2. And I'm gonna get a little lazy here. I'm not gonna apply any more points. You should actually. You should. I'm getting a little lazy. Like I should plug in 3 or 4. I mean -3 or -4, but it's okay. Because I expect the graphs to follow the asymptotic behavior. Why even have the asymptotes in the first place? I expect that to happen. And there's a graph.
How do you know that the other asymptotes are gonna be in the off like that.
Up and down?
Yeah.
My sign chart. Because to the right of 2, positive. That's what I know.
So just alternate every
Correct.
every break.
Correct.
Wait, have you found the examples of these times again? Just use the.
Whatever makes the top bottom 0. Those are my critical points.
Just all x and y steps. No.
Not the y-intercept. The x-intercepts and the vertical asymptotes. Right, because those are critical points. That's what's going to cause y to change sign. Right, because you're going to see that transition. Like if I go from 2.01 to 1.99, all of a sudden the x minus 2 changes sign.
Okay.
That's going to cause a change in whether I'm above or below the x-axis. Okay, let's do one more of these. Then I think we're good. Then you guys can do some homework.
Wait, x.
Vertical. Vertical. Where makes the top and bottom 0?
You know, like,
Mhm.
like down there.
Oh, because of sign chart. 1 to 2 is negative.
Oh,
So obviously when we plugged in 3, the whole thing was positive, right? And then I talked about how we'll do a bit alternation in signs because all these are current ones. So because we're positive right 2, I can't be down. See, actually, this is a great question Avery's asking. See, like on the far right, I have 2 options. I go up or below, above or below, right? I will not go below. If I go below, I'm going to create a new x-intercept. I can't have any more x-intercepts. The equation doesn't support that. So I have to go like this. I have no choice. And because of the alternation, this arrow's got to be pointing down, not up, because of the alternation in signs here. I can't do that. And plus, I need to touch this anyway, right? I need to touch it anyway. Then I have this here. And of course, I have to be to the left here as well, because between -2 and -1, I'm negative as well. Then positive to the left of -2, so I got to be up here. So what you're doing is you're trying to find all this evidence. It's highly analytical, actually. And this is high order, and people like throw out these fancy words like high order critical thinking. What does that mean? That is high order critical thinking because you actually have to think very critically what's happening. This is why many students here at the school they struggle with this. I mean, you guys are at the high end in pre-calculus. So I know you guys will be fine and comfortable, but we have to really tap into that type of thinking because you guys have that capability. You just got to use it. Some people don't have it developed and they struggle with this. And it's fine, but it's definitely a struggle because it's requiring so much more reasoning on your part and putting all the pieces together, make sure it all makes sense. Okay, let's try one more here. Y equals. Okay, let's do some factoring. You see all this like middle school stuff's coming into play now. This has got to be second nature factoring. X. What's that going to be? X plus 2x minus 1, I think. Is that right? Okay. So those cancel. So really it comes down to this. Okay, so far we're okay with the factor and simplifying. Is that okay? All right. So the VA, the HA, or end behavior asymptote is a better way of putting it, holes, x-intercept, y-intercept, in a sign chart. Okay, I think I did everything right. Okay, what's my vertical asymptotes here? And 0. What's my horizontal asymptote? Y equals 0. Are there any holes? There are. At 1 comma what? Perfect, good. Do I have an x-intercept? I have 4 comma 0. Or as an ordered pair this time. Do I have y-intercept? Nope. Because it's a horizontal, it's a vertical asymptote there. So, yep, okay, cool. I draw it better. And you can always check your work in Desmos, by the way. So I don't have an answer key. I don't think I do. I have to double check the binders for this stuff. I don't think I do have an answer key. But you can always check your work in Desmos too. We could talk about next week when we're back from the weekend. Yeah, I went -2 as well. There's a hole at oh, the horizontal asymptote also. Do you have an x-intercept at -4, 0? By the way, am I crossing my horizontal asymptote? I am. That's okay. There's not a problem with that whatsoever. Because you can set this equation equals 0, and there are some values of x that make that work, that make that valid. So that's totally okay. You totally could have that crossing. It's all about the ends of the graph. 1, 5/3, which is probably over here. Let's do the sign chart. If you put anything bigger than 0, like say 1, for example, what's going to happen? Well, not 1, sorry, like 2, because you can't do 1. Those 5/3. Yeah, it should be positive, right? If you're putting like 2, for example, or if you're putting like 0.5, whatever, it's going to be positive, exactly right. Does every factor occur an odd number of times? Yep. You have alternation in signs. So I expect the graph to look like this. I am gonna make a little table because I feel a little uncomfortable not doing a table. If I plug in -1, what do you get? Think so? Yeah, -3. Yeah, and it should be like this. You can't break the x-axis because you're gonna create a new x-intercept. And you're positive here. Then here, it's gonna dip below, but it's gotta come back up eventually and stay below. How low it dips, you've not learned that yet. You will get to that when we do more calculus. But yeah, that's kind of a funky one.
Did you plug in -1 to figure that out too?
Yeah, just to see exactly where that's going to be, that curve. Yeah, because I didn't feel comfortable just like drawing something crazy. Um, yeah, so I felt like, and -1's halfway between -2 and 0. That's why I chose -1. But I knew it was going to be negative in that interval. That I knew from the sign chart. So yeah, okay. So we got about another 15 minutes. So here's questions, by the way. We good? Okay. Yeah, go ahead, Lucas. Yeah.
Like, or on the left, doesn't cross, it actually crosses the x-axis.
Sign chart. Sign chart.
Why does it?
Sign chart. Well, to the left, -4 is negative. So between -4 and 2 is positive. So you have to cross.
Oh, it's making it.
Yeah, you have to. Yeah. The sign chart, I feel, is essential.
We don't know how much it crosses.
Well, how low it goes? No, because you haven't learned that yet.
Oh.
Yeah. So that's gonna be an estimate. That's calculus. So what you do, so actually I'll tell you right now, what you're really looking for, see how low it goes, is to see where the tangent line is horizontal. So tangent line is a graph, is a line that just grazes the graph. Like it's doing tangent lines of circles, just grazes a circle. So you're looking for a tangent line that's horizontal. That itself is a derivative, the slope of a tangent line.
And then when the slope is 0.
Well, the derivative is 0 or the slope is 0. But the problem is I'm not taught you that technique yet of how to do a derivative. But what you would do is you take the derivative of this, which you'll learn, you'll be able to do just fine, or the simplified form be easier. And then you see where it equals 0, and then you would know where it happens. But you've not learned that skill yet. We're not there yet. We will get there. Okay, so what I want you guys to do, yeah, I want you guys doing pages 22, 23, and 24. I'll write up to the margins here. And going back to the top, I want you doing B and C on page 2. Sure, why not? Of course I will. Okay. Um, page 4, part B. Is it really your birthday? Oh, happy birthday. How old are you now? 17. Nice. Congratulations. Um, page 6, number 3.
I think I thought of this. We're gonna post it.
I'm gonna post in a moment. Um, do we do example 7 and 8? Yeah.
Probably eight, yeah, get it out.
And we'll say example 9. Page 9, example 9.
Yeah. Finally.
Yeah, so that's what 5, 6, 7, 8, 9, 10. So 10 problems. I think that's fair. Yeah, that's fair. Yeah, that's gonna be the homework. I'll post the Schoology right now. Actually, I'll take a picture. So. Oh, weird.
I think you're right. I'm here. Cool.
Yeah.
How do you know that it continues down or not? So like I have all the, there's no absences and I agree understand. But how do I know that there's been?
Oh, the range is gonna be all real numbers. I mean, there's no reason why, except for that too. Yeah. Yeah, of course, yeah, yeah. Well, that's nice. You think so.
All right. So stop the recording.